Here's the Zoom meeting for Physics 231C, Friday, November 3rd, right here. So this week we've been studying gravitation, chapter 9. I forgot to record the Zoom meeting, so I'll make a little short recording here, and then I'll post this short recording on the YouTube channel. So for November, we'll start here with chapter 9, then 10, 11, then we have Thanksgiving, then exam 3 at the end of November. Then we're going into December, a couple more chapters, the beginning of December, and then the final exam, I believe, is located here. Thursday of exam week. That's not our choice. That's determined by the registrar's office. Now, when you read chapter 9, you need to remember to take notes. So here's some of the notes you should have already in your notebook from reading chapter 9. The first section was on Newton's law of gravitation. This is really the fundamental equation for this chapter. The gravitational force, when there are two objects exerting gravity on each other, the force on either object is g m1 m2 over r squared. It's an example of Newton's third law. There are equal but opposite forces on either object. Both objects attract the other object with a force which is the same magnitude, but in the attraction direction in the two cases. Then there's a section on planetary motion. Before Newton, Johannes Kepler determined how the planets revolve around the sun in the solar system. Planets revolve on elliptical orbits. The sun is not at the center of the orbit, it's at the focal point of the orbit. The radial vector sweeps out equal areas in equal times, and Kepler's third law, the square of the period is proportional to the cube of the radius. And Newton went beyond what Kepler had. Kepler only knew from astronomical observations that a cubed over t squared is the same for all the planets. But Newton proved, what is that constant? What is that constant value? It's based on his law of gravitation. It's 4 pi squared a cubed over g times the mass of the sun. The mass of the sun is the same for all the planets. So the period only depends on A, the semi-major axis of the ellipse. There's a section on the gravitational potential energy. The force goes like 1 over r squared. The potential energy goes like minus 1 over r. Then there's a section on artificial satellites, and there'll be some problems involving artificial satellites on the homework and on the next exam. And then there's a section 9.5 about other aspects of gravitation. For example, ocean tides are caused by gravity of the sun and the moon. So the ocean tides on Earth were known by all seafarers, but not understood. The first person to understand the tides was Isaac Newton. As the moon and the sun pull on the oceans, there are high tides on opposite sides of the Earth. And then there's a short section about the breakdown of Newton's theory of gravity. Newton's theory of gravity is extremely accurate. So NASA, when NASA has to do a calculation involving gravity, They just use Newton's theory. That's accurate enough for their purposes. But for very accurate astronomical observations, a more accurate theory of gravity has to be used. That was developed by Albert Einstein back in the early part of the 20th century. And that's called the theory of general relativity. And there's some phenomena in the universe which rely on Einstein's theory. For example, black holes. Black holes have no connection to Newton's theory. They're entirely explained in terms of Einstein's theory of relativity. And you should also read chapter 11 in the secondary textbook, the textbook Unifying the Universe, which is all about Newtonian gravitation. Now, problem set 7 is due Monday. There are a bunch of problems on gravitation taken from chapter 9 of the textbook, and the hints for those problems are on the supplemental content in the usual place. But now let's look at a couple of other problems, hints for a few other problems. So again, you should have the important equations written down and the ideas written down in your notebook. So here's sort of a brief description of chapter 9. And this is the important equation. The force is a universal constant G, which is the same for any two masses in the whole universe, times the product of the two masses, times the square of R. R is the distance between the two masses. Or if we think of the two masses as spheres, it's the distance between the centers of the spheres. That's the magnitude of the force. As for the direction, it's directed towards the other mass. So it's an attraction. Here's a hint for a problem which is on the assignment, problem 39, which concerns the Cavendish experiment. Henry Cavendish was the first person to measure G, Newton's gravitational constant. Cavendish lived some years after the life of Isaac Newton, so it wasn't until 1800. What's that, about 70 years after the life of Isaac Newton, that someone was able to measure G. That was Henry Cavendish. So as in any problem, the way to solve it is to draw a picture. So here's a picture, or actually two pictures, which shows Cavendish's torsion balance and the masses on the torsion balance attracted to large lead spheres, which he had placed in his laboratory. The lead spheres exert a torque on the balance, and Cavendish could observe the acceleration of the torque. The acceleration of the balance. And you know, torque and angular acceleration are related. That was chapter 6. So the problem is to calculate this force. Well, that's easy enough. That's Gmm over d squared. I didn't label d. This distance is d. It's 1/2 the length of the rod, so d would be 19 centimeters. The answer to part A is Gmm over d squared, where this m is the large lead sphere. Little m is the small lead sphere at one end of the torsion balance. G is a universal constant, which is what Cavendish was trying to measure. And d was the distance between the centers of the masses, spheres m and m. And then part B of the problem is to calculate the torque. Well, torque is distance times force. So the torque due to this force is R times F, but there's also a torque due to this force, which is another R times F. They both pull in the same direction for rotation. So the torque is 2 times R times F. So on all problems, we start by drawing pictures, we write down a few equations, then we pick up a calculator. Here's problem 53 from chapter 9. It's again assigned on the homework assignment. It's the Hohmann transfer orbit. Suppose NASA wants to send a satellite from the Earth to Mars. They do that every so often. They can only use a certain amount of fuel. They can't use too much fuel. So they want to send the satellite from the Earth to Mars using the minimum amount of fuel. This is a problem that was solved by Herr Hohmann back in 1925, before there were any rockets. He worked out how would be the most efficient way to send a satellite from the Earth to Mars. Well, you would put it into a orbit around the sun. Now, revolving around the sun is on an ellipse. So you'll put it on an elliptical orbit where the perihelion is the distance from the Earth and the aphelion is the distance from Mars. And you time it right so that when the satellite reaches the radius R2, Mars will be there. So you sort of have to send it off when Mars is about here, and then as it's moving around on the Hohmann ellipse, Mars will be moving around on its orbit, and they'll meet. Now, the problem is to calculate the travel time. Well, the time here is just the period of revolution, or actually half a revolution, because you only want to go from Earth to Mars, not back to Earth. So half a period on an elliptical orbit where the semi-major axis of the ellipse, the major axis of the ellipse, the large diameter, is R1 plus R2. So the semi-major axis is 1/2 R1 plus R2. And now period and semi-major axis are related via Kepler's third law. So you can calculate the period here. And then 1/2 of that will be the travel time. And then finally, problem 77, satellite is in a circular orbit 1,000 kilometers above Earth's surface. So we start by drawing a picture. Here's a picture of the Earth. It has a radius capital R. The satellite, it has a distance h above the Earth. So that's the height of the satellite above the surface. The radius of the satellite's orbit is little r, which is the radius of the Earth plus h. And there is the picture. Now we have the equations. This is the equation for the circular orbit. Mass times acceleration is force. That's Newton's second law. What mass? The mass of the satellite. So I didn't label it. I should have labeled this mass as m. And this mass is capital M. So mass little m times the acceleration. Now the acceleration in a circular orbit is v squared over r. That's the centripetal acceleration. So there's mass times acceleration. That has to equal force. Well, the force is the force of gravity. And the force of gravity, let's say the satellite is here, the force of gravity will be directed towards the center of the Earth. And its magnitude is gmm over r squared. So there's one equation we need. And then we're given the information on the total energy, the total mechanical energy possessed by the satellite. So we need to get an equation for the total energy, since that's something we know. E is kinetic energy, 1f_mv squared, plus potential energy. The potential energy is negative gmm over r. The force is gmm over r squared, but the potential energy is gmm over r times -1. So here's just the energy. Gravitational force is conservative, so energy is constant. So this will be the same value any point around the orbit. Now we can get one more useful equation if we notice that by the first equation, mv squared, I can cancel 1 power of r. So mv squared is gmm over r squared times r. So this term will be 1/2 gmm over r, and then minus gmm over r. That'll be minus 1/2 gmm over r. So, I have these basic equations, and then by algebra, I have these other useful equations. And now I'm ready to start calculating numbers. So I have to, get my calculator out. First, I have to use a little algebra. I know E, that's given. I know R, that's the radius of the Earth, plus the height, 1,000 kilometers above Earth's surface. So in this equation, the only unknown quantity is the mass of the satellite. What about G times M? Well, G is a universal constant, M is the mass of the Earth. So both of those are known. In fact, I can simplify the calculation by realizing that G times the mass of the Earth is little g times the radius of the Earth squared, right? G is the acceleration due to gravity. Well, that's the force divided by the mass. So the force divided by mass is gm over r squared. R is the distance from the center. The distance from the center of the Earth is just the radius of the Earth. So when I need to do a calculation using gm, I can simplify things by just using little g, 9.81, times the radius of the Earth squared. And there may be some cancellations, or anyway, I know the radius of the Earth, it's 6,371 kilometers. So anyway, this equation, the red equation, the unknown is m. So that's part B. I can calculate m. Okay, now I know m. Now I want to know the kinetic energy. That's part A. Well, the kinetic energy will be 1/2 mv squared. So the kinetic energy is 1/2 mv squared. But by this equation, mv squared is gmm over r. And minus 1/2 gmm over r is E. So the kinetic energy is negative E. Or I could just say the magnitude of E. So that's part A. Now, part C is to calculate the speed. Well, that's easy because 1/2 mv squared is k. So I can just solve for v, 2k squared of 2k over m.